Hi everyone, I wanted to make some videos on Kepler's laws because they are a small part of the AP Physics exam. You'll probably get like one or two multiple choice questions on them. So let's jump right in with Kepler's first law. So for his first law, this is probably the least likely to be on the exam. This is just more of a qualitative observation. But Kepler's first law says that all planets move in an elliptical orbit with the sun at one focus. So if this is our orbit of our planet, and let's say this is our planet, then we'll have the sun at one focus, and then we'll have some second focus. Okay, so for Kepler's second law basically says that if we have a planet moving in an elliptical orbit, and then we'll of course have our sun at one focus, the area that the radial vector of the planet going from the sun out to where the planet is orbiting, the area that it will sweep out in a certain time period will be equal for all time periods of the same amount anywhere in this elliptical orbit. So the way we can visualize this is, let's say we have our planet, and this is at position 1, and then it's sweeping down to position 2 in time t. Then if we were to draw the radius vector going from the sun out to the orbit, and we were to find this area, let's say this is area 1, then if we were to have this planet, let's say at position 3, moving to position 4 in time t, then the area formed in that going from the sun out to the orbit in that amount of time will be equal to the first area. So we basically get that our area 1 is equal to our area 2. Okay. The second part of Kepler's second law is the idea that when a planet is closest to the sun, it will be moving the fastest, and when it's the farthest away, that's when it's moving the slowest. So we can visualize this if we have our elliptical orbit and we have the sun. Then let's say we have our planet. This is it when it's at the position closest to the sun, and here it is the farthest. So we can call this distance small r, and this one will be capital R. So we can use conservation of angular momentum to determine that the planet must be moving the fastest when it's closest to the sun and slowest when it's farthest away from the sun. Because if we say our initial angular momentum must be equal to our final angular momentum, we can say that angular momentum is defined by the mass of the planet times its speed at small r times small r, and that must be equal to the mass of the planet times its speed at capital R times capital R. And this is because there are no external forces acting on this system, so momentum will be conserved. So we can cancel out the mass of the planet. And so what we see is that when R is small, like it is here, our speed must be the greatest. So we could say that we would have a fast speed times a small radius must be equal to, well, when r is really big, our speed must be small in order to be equal to our speed being fast and our radius being small. So we can say that this is equal to a small speed times a large distance. Okay, now moving into Kepler's third law, this is definitely the most likely to be on the exam, because this is the most quantitative law and, in my opinion, the most interesting. So what Kepler's third law says is that if we have a planet, first I should say, you've probably seen Kepler's third law as t squared over a cubed, a being astronomical units, or we could say t1 over a1. That must be equal to our period squared over our distance squared cubed. So that'll be proportional for a planet. But the way we can derive this is by saying if we have some planet P, and let's say we have, this is the orbit of let's say some satellite S, moving around our planet P, then the only force acting on this satellite in the system is going to be planet P. So if we were to draw a force diagram for our satellite, all we would have is the force of the planet on the satellite. Okay, so now in order to derive Kepler's third law, what we can say is using Newton's second law, which is sum of the forces, or a net force, must be equal to our mass, in this case of the satellite, times our acceleration. So this satellite is moving in a circle, so we're going to have a centripetal acceleration. So now what we could do is we have to define the force acting on our satellite. And in this case, because the planet is the only force acting on our satellite, we can use the force of gravity. So we could say capital G times the mass of the satellite times the mass of the planet over r squared. This is the distance from the surface of the planet to the satellite. This must be equal to the mass of the satellite times the definition of centripetal acceleration, which is speed squared over radius. So now we can clean this up a bit, and we can get rid of our mass of the satellite, and if I just multiply by r on both sides, we get the gravitational constant times the mass of the planet over r must be equal to v squared. Okay, so now what we can think about is we can substitute in for v squared. We can use the definition of speed because we want to get this down to a relationship between period and distance. So if we say speed is equal to our change in position over our change in time, well, our change in position is going to be equal to our circumference because the circumference of this orbit is the distance that this satellite is going to be traveling. So we could say this is equal to 2 pi r because that is circumference. And then for our change in time, well, that's just going to be the period of the satellite orbiting. So what we could say is velocity is equal to 2 pi r, and that's measured in meters, over our period, which is measured in seconds. And then we get the correct units of meters per second for our speed. So now if I sub this back in, I get g, mass of the planet, over r is equal to 2 pi r over period squared. So now what we can do is if we square this, we would get 4 pi squared r squared over period squared. So now what we can do is rearrange this so that we actually get a relationship that shows that period and r are proportional. So we could say that t squared is equal to, if I multiply both sides by r times r, then we would get period is equal to 4 pi squared over gravity times the mass of the planet times r cubed. So basically what we're getting is that period squared is going to be proportional to our radius cubed. So this is the relationship for Kepler's third law. Okay, those are all of Kepler's laws that you'll need to know for the AP exam. I hope this video was helpful, and I'll see you next time.